people as well, and this is actually like the culmination of Georg's thesis. Unfortunately, Georg can't be here today because it's his first day at work in his new job at Google. So while his old boss and his new boss are enjoying themselves at ICFP, this poor guy actually has to work today, but I'm sure Derek will almost give us a little presentation.
Can everyone hear me? Yes? Great. Okay, so good morning, everyone. I'm Derek. As Andreas said, Georg is really the driving force behind this project. So I would have liked him to be able to give this talk, but I'll do my best to do it in his place. So I'm going to tell you about Pilsner, which is the first compiler for a higher-order imperative language, by which I mean something like an ML-like language, that has been compositionally verified. And basically what I want to do is tell you what that means and why it was challenging and how we did it. So the starting point for this work is this whole field that's developed in the last decade, in particular on compiler verification. So particularly since Xavier's work on the CompCert project. So the basic goal of compiler verification is to formally guarantee that the output of your compiler preserves the semantics of the input. And usually, well, traditionally, what that means is that if you have some source program PS in the source language of your compiler and you compile it down to a target language code, then the target language program PT has the same observable behaviors that would be allowed by your source language. Okay, by running PS in the source language semantic. And this has various benefits, but the main point is that if you do some verification or you do some analysis on your source program, then you know that the behaviors you've proven to be correct will also hold for the target program. So the main limitation of this traditional notion that we're addressing here is the fact that it doesn't say anything about separate compilation. So it only talks about what happens when you compile a whole program PS down to the target language. And so there's been a lot of work in the past 7 years or so on what people call compositional compiler correctness or compositional compiler verification. And basically what that means is trying to define some notion of semantics preservation that applies to the separate compilation setting that is definable at the level of separately compiled modules. And there's different people have different takes on this. If you ask Amal, for example, you'll get a somewhat different story. But from our view, the three key criteria for a notion of semantics preservation are what we call modularity, flexibility, and transitivity. So let me try to explain what that means. So modularity is sort of this basic criterion which says that your notion of semantics preservation should be definable at the level of individual separately compiled modules and preserved under linking. So for example, if you have a source program which has 3 modules, S1, S2, S3, and you compile them separately using your compiler, your verified compiler, to target modules T1, T2, and T3, then when you link the target modules together, the behaviors you can observe there are included in the behaviors you can observe for the source program, or for the linked source program. The second criterion, flexibility, just means that your notion of semantics preservation should not be tied to a specific compiler. Okay? It should be capable of verifying a wider range of program transformations. So, for example, you should be able to verify multiple different compilers for the same language. And you should also be able to verify hand-optimized code. So, for example, you might have some module which you've S3 in your source language, which you've implemented at the target level in some particular hand-optimized way, and you want to verify that that is a correct transformation. And again, when you do this, it should be done in a modular fashion, so you can link together these target language modules, and it preserves the semantics of the linked source modules. The last criterion is transitivity. So when you're verifying a compiler, of course, a compiler is not a monolithic transformation. It is a compositional transformation consisting of multiple passes. So you should be able to verify each pass of the compiler separately and then link them together transitively to get an end-to-end correctness result for the whole compiler. So basically, what's the problem that's not addressed by prior work? Well, in prior work, there have been a number of techniques proposed for this kind of compositional compiler correctness, all of which satisfy this basic criterion of modularity. But they are all either not flexible enough in our view, or they're not transitive. Okay, and so you can basically understand what we're doing. Well, you can guess what the next slide is going to say, which is that we figured out how to get all three. So our sort of central contribution is a new way of defining semantics preservation for compiler correctness, which we call parametric interlanguage simulations, or PILs, rather mouthful. And the point being that it satisfies all three of these criteria together. And this is not just a sort of theoretical construct. Okay, we've actually mechanized Pils in Coq and used that to verify Pilsner, which is a simple but non-trivial multipass compiler for an ML-like language, and the first such compiler to be compositionally verified in the way that I've described. So let me say a little bit more about Pilsner. So basically, Pilsner starts with an ML-like core language. This is kind of a core lambda calculus with products and sums and recursive types and abstract types, polymorphism, and mutable references. So a bunch of the features you see that are sort of typical of ML-like languages. And it goes down to an idealized assembly language going through a CPS-based intermediate representation. And at the CPS level, there's a bunch of optimizations that are performed. Nothing too complicated, really, but inlining, quantification, dead code elimination, and hoisting, among others. But the point of, as I showed you before in this picture, the point is not just that we want to develop a technique for a particular compiler. We want to actually demonstrate we have a more flexible method. So we've used Pils not only to verify this one Pilsner compiler, but also to verify another compiler, which we call Zwickel, which is another German beer, in case you're not an aficionado. And it's a direct translation, which does not go through the CPS intermediate representation. It's a very simple compiler, but it's to demonstrate that we can handle different compilers. And in addition, we've also verified a kind of challenge example from the literature, which is a higher order ML function that's implemented at the assembly level using self-modifying code. Now, the point of that example is not that this is a realistic thing that you're going to actually do, but to demonstrate the flexibility of Pils, that we can really handle a really wide variety of different kind of program transformations and still link together the results correctly. So for the rest of the talk, I'm not going to really talk about the Pilsner compiler itself. I'm going to instead focus on this parametric interlanguage simulations, or Pils, which is really the secret sauce behind the whole the whole thing that makes our verification effort work. And I think because it also has a very interesting history. So Pils is building on a sort of mountain of prior work. If you really want to understand at a deep technical level what's going on, it helps to have a PhD in compiler correctness, step indexing, logical relations, game semantics, and bisimulations, for starters. But it's not really necessary in order to get a sort of high-level view. So in this talk, I'm not going to talk about that stuff. I'm going to instead focus on the two most direct influences on Pils, which are two papers that we published previously in Popple, which as this picture suggests, I sort of view as the barley and hops that goes into our Pils. And I mean that sort of metaphorically because they're because they are really like the key ingredients, which on their own are not very tasty or satisfying, to be honest. But when combined in the right proportions and fermented with years of a graduate student's life, you end up with a delicious and tasty beverage, which is our final result. So I'm going to focus mainly on explaining sort of what we were trying to do in these two papers, where they fell short or where they were lacking, and how they usefully complement each other. And that's why we're combining them. So to lead into that, let me start with a sort of straw man approach. Sort of what's the most obvious thing one might think of as in defining a notion of compositional semantics preservation, and that is contextual equivalence. So contextual equivalence is kind of the canonical notion of program equivalence that people have studied, and the idea is that two modules are contextually equivalent, M1 and M2, if any client program that you link them with cannot tell the difference between them. All right, so any context C with a hole in it, if you fill that with M1 or you fill that with M2, you get programs with the same behaviors. And the reason I would say that people like contextual equivalence so much is that it really hits all the three criteria that I mentioned earlier right on the head. Okay, so it's inherently modular and transitive. This is easy to show by definition of contextual equivalence. It's also very flexible in the sense that it's extensional. It doesn't say anything about why you can transform, what specific transformations are allowed. It just talks about, that you can't tell the difference between the modules. The Achilles heel of contextual equivalence, however, is that it's fundamentally a single language notion. Okay, so it doesn't say anything. Because you have to link M1 and M2 with this same context C, it means that M1, M2, and C must all be interoperable in the same language. Okay, And so this seems to, at a first glance, mean that contextual equivalence is simply not applicable to compiler correctness, where we're linking where we're relating the high-level source programs with low-level target programs. So, when we started thinking about this problem about 5 years ago, our thought was that, well, instead of trying to use contextual equivalence as our notion of semantics preservation, let's do the next best thing and use a proof technique for contextual equivalence that does not suffer from this single language restriction, and that was logical relations. So in our initial work on this, we looked into using logical relations. Logical relations are a classic proof technique for many things in semantics, but one of them is for proving contextual equivalence in functional languages. And in the past decade or so, there's been a big advance in sort of more sophisticated versions of logical relations called step-indexed crypty logical relations, which allow you to scale this technique to imperative functional languages like ML. What's interesting about it, though, as I said, is that for the purpose of compiler verification, is that logical relations, unlike contextual equivalence, scale naturally to support interlanguage reasoning. So let me give you just a very high-level understanding of why that's the case. So if you look at sort of the canonical thing you see in any logical relation anywhere on the planet, it has some clause like this. All right? It says that you have, for defining when two functions are logically related. It says f1 and f2 are logically related at the type A or B if, for any arguments, v1 and v2 that are related at the type A, applying f1 and f2 to v1 and v2 is related at the type B. And the thing to notice here is that although these could all be terms in the same language, they don't have to be. So when you quantify over v1 and v2, the ones and the twos sort of all stay on their own sides of the relation. And so it's actually well known that you can use this kind of logical relation to relate different things, different languages or different semantics. For example, when you're proving adequacy of a denotational semantics with respect to an operational semantics, you're relating two different semantics for the same language. So what we did in this POPL 11 paper was essentially take this idea to its extreme and show that you could use this to also relate high-level ML code with very low-level, untyped, unstructured assembly code. And so on one level, this was kind of a natural thing to do. At a technical level, it was challenging because you had to figure out how do you map concepts like values, continuations, function application, what does F2, V2 mean at the assembly level. But OK, we did that. And the advantage was we got a technique that, like logical relations, is inherently modular and very flexible, supporting a variety of different transformations. The problem, and it was a big problem, was that the technique was not transitive. So logical relations proofs in general, especially crypty logical relations proofs, cannot be transitively linked together. And so as a result, we had a technique which would support a verification of a single-pass compiler, but not multi-pass compilers. And so, I mean, I was very proud of this paper, but on the other hand, at the end of the day, it was like a bit of a bummer. Because that's, in case you don't know, that's the dude from The Big Lebowski getting to the end of our POPL 11 paper. And that paper is best read while high, actually. So what did we do? So fortunately, we did come up with a technique for getting around this, and that's what we addressed in this POPL 12 paper. So basically, by adapting some ideas from the literature on bisimulations, we were able to come up with a new technique, which we called parametric simulations. And the idea with parametric simulations is basically to have something that supports all the kind of reasoning that you do with crypty logical relations, so to have the kind of expressive power in crypty logical relations proofs, but where the method would additionally be transitive. And to explain at a detailed level how this works is beyond what I can do in this short talk, but I will try to give you the key idea. So the key idea is basically that logical relations are so beautiful, so concisely and elegantly defined, that they admit a few too many proofs. Okay, so they allow you to prove things. They permit certain kinds of proofs that you would never actually do in practice. And because of that, the space of proofs that they admit is so large that it becomes difficult to prove this kind of transitivity result. And so the idea with parametric simulations was to restrict the method so that it would only permit the kind of proofs you actually do, thereby imposing this more rigid structure on the proofs that makes them easier to link transitively. So let me try to illustrate this at a high level with a simple example. So suppose we want to prove that these two higher order functions are equivalent, okay? And they're very structurally similar, right? So they both take some callback f of type A or B, and they call it on some argument v, and then they do something with the result. So how do you prove this using either logical relations or parametric simulations? Basically what you do is you first assume, as I showed you before, how we define logical relations for functions. We assume the arguments are related, the f1 and f2, and we have to show that the results are related, the let expressions. Now, how do we show that the let expressions are related? Well, we don't know anything about f1 and f2, so the only thing we can really do is use the fact, or the assumption, that they are logically related, which tells us they take related inputs to related outputs. So we can reduce the proof burden to showing two sub-goals. One, that the inputs to the f's, the v1 and v2, are related, and then showing that if we assume the outputs are related, which we're allowed to assume, then the continuations e1 and e2 are related as well. Okay? So that's how you would do the proof using logical relations. And you'll notice that that proof is what we call parametric in the f's. Okay? So what do I mean by that? I mean that we never looked into the f's and said, what are the possible f's that could satisfy this logical relation? We just said, we assume they're logically related, and based just on that assumption, we do the rest of the proof. But logical relations also allow you, in theory, to do non-parametric proofs. In other words, proofs where you actually did a case analysis on the f, and if f was lambda x whatever, then you do one proof of why the let expressions are equivalent, and if it's something else, you do some other completely different proof. And that means that the proof space is just too unstructured. So essentially what the idea of parametric simulations is that it forces you to do that parametric proof that I showed you. Right? That's the only proof that would be allowed in establishing this equivalence. And as a result, the proofs have a more rigid structure, and you can prove the transitivity. So putting everything together, basically in the Popple 12 paper, we developed this initial idea of parametric simulations. And we proved this transitivity result, which turned out to be a bear. But that was already complicated enough just in reasoning about single language contextual equivalence. So we just developed that in the single language setting, and we claimed that this should scale, like logical relations do, to handling interlanguage reasoning. But we didn't actually work that out. So essentially what this paper is doing is taking the interlanguage reasoning framework that was developed in the Popple 11 paper and swapping out the Kripke logical relations bit with parametric simulations. And so as a result, getting parametric interlanguage simulations, which marry the benefits of these two approaches. So I have, am I out of time, or is there 1 minute left? All right, well, all right, so I'll briefly say something about related work. So I just want to mention this other related work, a different approach on using multi-language semantics. So this is a very different style of how you attack the problem, basically where this is work by Perkanti and Ahmed in ASOP 14 and this compositional concert work in Popple 15. And the idea there is just that the idea is basically to stick with contextual equivalence by merging all the languages of the compiler into one multi-language semantics so that the source language, the intermediate languages, the target languages all can interoperate. Okay? And basically the advantage of this is that it gives you support for multi-language interoperability. All right, so we're not trying to do that here. We're just addressing compilation of a single source, high-level ML-like source language, whereas they're talking about verification of compilation for multi-language programs. The drawback is that it limits flexibility to some extent. So, for example, in the ASOP 14 paper, you can only link together the results of different compilers that have the same intermediate languages, and those languages, all the languages of the compiler have to be typed, whereas we don't have any such restriction. And in the Popple 15 paper, basically all the languages of the compiler have to share a common memory model, which is fine for a C compiler, which is what they're doing, but I don't think it would scale to an ML compiler. So with that, I'll conclude and take questions. Thanks.
Hi. So thank you again for your beautiful talk, because now I understand what you have been doing since for the past 3 or 4 years. We were competing at here on verify separate compilation, and at least we lost, but I'm not sure yet who between Princeton and you and Amal Ahmed really finally won. At least I can. My question is the following: you are doing interlanguage compilation. But how hard would it be to combine your work with at least Per Conti's work to get both inter-language and multi-language at the same time?
Yeah, so that's a very good question. I don't know. I mean, I don't see any fundamental reason why you couldn't use the basic, this basic infrastructure of, I don't know why you couldn't use the basic infrastructure we have for multi-language compilation. You just have to instantiate the source language with a source language that itself supports multi-language interoperability. I don't see any fundamental reason why that can't be done, but I mean, I didn't see any fundamental reason why this paper couldn't have been written, when we were doing the work 3 years ago. So this stuff is hard to actually make happen.
Okay, thank you.
Maybe you could elaborate a little bit on how transitivity fails in the earlier approach?
Yeah, so this is difficult to say. I think I'd have to take that question offline. I mean, I can show you sort of technically where it shows up in proofs, and there have been a couple attempts to get transitivity. So Amal has a paper from ICFP 06 where she gives she proves transitivity for a restricted pure language with recursive types. But the technique there relies on adding syntactic types into the logical relation, which is something we explicitly did not want to do because we wanted to handle untyped intermediate languages and assembly languages. There's also a paper by Lars and one of his students, Lars Birkedale and one of his students, that proposes another way of getting transitivity. But again, that approach that basically bakes in that both sides are in the same language. So I don't know of any. It's a very good question. I've kept asking this question to various people, but there doesn't seem to be a very, very crisp answer as to exactly why it breaks. Aside from the one that I sort of gave the intuition for before.
Okay, let's thank Derek again.
Oh, I'm a little confused because you're relating languages untyped. You're not using the type to relate them. Can we go back to the slide where you talked about contextual equivalence and where you colored red and blue?
Sorry.
Yeah.
All right. Yes. This one?
No.
With logical relations. Okay. This one.
Yeah, this slide. What are these types on the right, and what color should they have?
Right. So we do use types even in pills as the sort of to describe the contract that must be satisfied between the two languages. Even if the two languages are untyped, you can still use a type to sort of specify what
Okay,
kind of
so there's like a type system above them.
The type system, it's sort of, it's like you can think of it as the specification for the linking, effectively.
Okay, thank you.
Okay.
Okay, thank you, Derek.